So let's consider the topic of standard reduction potentials. Now, what we're going to do, notice that in a video we had posted for solving a problem, we've already seen this half cell. And I'm actually going to go straight through the salt bridge and through this half of everything. We've seen this half of it set up. It's just we had it over on the other side a minute ago. And that's just helping us spot that, okay, as configured, the electrons will actually be flowing from this cell over. Now, I want to just point something out too. Suppose we had this whole setup reversed. What if we had put this hydrogen gas setup over here, and we put this exact same beaker over here instead? Well, all that's going to happen is our voltmeter is going to be reading the opposite voltage, which is just going to tell us that the electrons aren't spontaneously flowing from the silver to the hydrogen. The negative sign is telling us, hey, look, the electrons are flowing the other direction. And since we like keeping it in this standard format whenever we can, instead we went ahead and we drew it on this side. That's really kind of the approach that we use. You can just hook them up and see what the sign is on the voltmeter, and then when you draw it, just to keep things in the proper context and format, we'll go ahead and just put whatever one is supposed to be the source of the electrons back over onto the left-hand side. Okay, but let's take a look at this. We actually have a lot more information than we were given last time. And you can see that showing up down here in our cell notation. Let me get rid of the ink. You can see that just looking at this notation, we know we go from a solid platinum wire, we see that right down here, to having H2 gas bubbling across with its activity equal to 1. Now, let's just remind ourselves what that means. When activity is equal to 1 and you're a gas, that means that you've got to be at 1 bar of pressure, which is crudely speaking about 1 atmosphere. So we have that fulfilled, and because the activity is going to be 1, we don't have to worry about activity coefficients or anything like that in this description. Now, if we were trying to build it, we might have to care about that, but we aren't going to need to worry about it right now. Activity is always the right way to describe the concentration of something in a solution. Molarity is just the best approximation experimentally of that, without having to do any extra math. So you see that we have our hydrogen gas bubbling across that surface, just like this told me was happening. The next thing that happens on the other side of my bubble is that I encounter an acidic environment. And this concentration of acid will have an activity equal to 1. Activity doesn't usually have units, but we do know that activity coefficients are typically going to be around 1. So we'll just pretend that we're in a dilute enough solution that activity coefficient was 1. That means molarity is about 1. But we'd have to be a bit more specific than that if we're doing high quality work. So molarity roughly 1, activity exactly 1. Then we have our salt bridge. Then you see that we hit another solution of silver ion with an activity of 1. And then we have a bar of silver metal. Now, when we hook all that up, what we're going to see is that the difference between these two cells is going to be 0.799 volts under standard conditions. So under these exact concentrations that I have listed there, we get this voltage. Now, these are experimentally, at least conceptually, really easy to set up. If we're bubbling hydrogen gas through, it's going to be limiting itself to a pressure of 1 bar because it's not a closed container. It's not going to build up any pressure. So that's going to take care of itself. We can make this acidic solution pretty straightforward in order to have this activity coefficient, this activity, when we multiply concentration times activity coefficient. We can plug a salt bridge into that, no big deal. We can set up our silver ion to also have an activity of 1 and stick a piece of silver metal in there, assuming of course we had silver metal. We connect the wires and hey, everything's there. That's not difficult to set up experimentally, as long as you're in a fume hood and you're not worried about that hydrogen gas exploding. So, okay, maybe there is a little bit of an issue using this standard setup over here. Well, it was one of our first ones we set up experimentally, and it does a nice reproducible job. It doesn't take a whole lot of experimental skill to build this thing, and so this became a standard. This is the standard hydrogen electrode. Now what we did is we decided it would be great to actually measure just about everything under the sun against this electrode under some standard conditions. So standard conditions would be where we have an activity of 1, and we're at 25 degrees Celsius. Under those standard conditions, we get this potential for the reaction that we have over here, this half-cell reaction. Now, when we arrange that so it is set up to be a reduction, notice we go, reduction is gain. Oil rig, reduction is gain of electrons. If we configure this to be written as a reduction potential, and we associate the value that we read when we set the thing up experimentally like this, we have a voltage for this under standard conditions. It's always good to put a sign with these anyway. That's what we're talking about when we say standard reduction potentials. You'll have a big long table of these at the back of your textbook, and we have an even longer table of these in our equations booklet, but we need to be very careful when we use these, because these are only applicable under this very, very specific set of reaction conditions. Only when we actually have everything in these concentrations specified, or better yet, activities specified. We have to be under really specialized conditions for that, but we often won't be. So what we need to be able to do, we need to be able to take these standard reduction potentials, which we'll summarize as E naught, and we need to be able to convert those using experimental scenarios to predict what the actual current voltage will be. That's going to be something that we're going to see in some of our other videos.